Thank you all for coming. This is the last panel in Princeton. We're going to be moving to the new building for all the future panels. I would like to thank our panelists for coming, Dr. Hunter, Dr. Barry Dunning, and Dr. Thomas Gillian. Dr. Randy Hewlett will be joining us shortly. And Brian will be moderating. And enjoy. And there is a sign-in sheet. Please just pass it around and put your name. Thank you.
All right, everybody, I'll be the moderator. So we're going to talk about AMO physics here. Of course, I work for one of these guys, so I can ask him my questions at any time. So if you have your own questions, please just kind of raise your hand and we'll call in. But to begin with, will you guys introduce yourselves and kind of talk about what types of research you do?
Okay, so I'm Tom Killian, and I've been here at Rice for about 10 years. And I have several different experiments. The general theme is studying matter under extreme conditions. And the extreme conditions I study is of cold. So matter behaves in a lot of different ways when you get things super, super, super cold. That teaches a lot about fundamental properties of nature, but also is in the pipeline towards applications and useful things for society. And I think AMO has always kind of made a nice balance between very, very fundamental, answering big questions, but also being connected to things that actually make a difference in our world on a relatively short term. And so the particular things I'm studying are ultra-cold plasmas. We make plasmas that are less than a Kelvin, which is super, super cold compared to like the sun or a candle flame. So it's a very exotic system. And then ultra-cold neutral atoms, we're advancing the techniques for making atoms cold and studying quantum regenerate gases and how what kinds of interesting states of matter we can form at these very, very low temperatures.
My name is Barry Dunning. I too am an AMO physicist. I've been here about 4 times as long as Tom, but I would never admit to it. I study principally atoms in highly excited states. So I'm dealing with atoms who have a principal quantum number n of the order of often 300 to 600. So these are physically very large systems. Their dimensions are macroscopic. In other words, an atom with n equals 300 is about 10 microns across. So I'm studying very, very large atoms, very weakly bound atoms, very fragile atoms. My interests are threefold. In one series of experiments, I'm trying to control the wave function, the electron wave function in the atoms. We have succeeded, for example, in creating a localized wave packet, just a little wave packet that moves around in a circle, kind of like a Bohr atom. So we've been trying to replicate some of your classical models of atoms in very high-end systems. We have been interested in atoms, how atoms interact with surfaces. So we've been looking, we were thinking we were actually doing atom surface interactions, but actually what we discovered is we have a very good way of looking at stray local electric fields in surfaces, which is now important for people who are trying to do quantum computing and things, trapping ions and atoms very close to surfaces. They can be quite strongly perturbed by these electric fields. Also, we started using Rydberg atoms as an ultra-low energy electron trap. Classically, the electron is often a very large orbit with very small amount of kinetic energy. So its effective temperature is about 30 millikelvin as regards its kinetic energy. So we can look at collisions, electron collisions at energies much lower than you can do any other way. So we've discovered all sorts of exciting things. We've created novel species like dipole-bound negative ions where the electron is bound on the dipole, not on a net charge. We are now looking at highly excited heavy Rydberg states where you've got a positive negative ion pair, very weakly bound orbiting at large distances. So those are the kinds of things that we've been working on.
My name is Han. I came to Rice in 2003. I'm the only theorist here in this panel. I'm interested in theoretical optical atomic energy. So we study the behavior of neutral atom molecules at very, very low temperature. Well, quantum statistics are very important. We study how these systems interact with photons, with light. And what are the normal quantum many-body phase that the system become when you cool the temperature down or when you put them in various different environments, such as a single trap or a periodic trap, trapping potential. So many of the work are very closely related to two collateral exponentialists here. So there is a very, well, in AMO physics, there is actually a very good synergy between theory and experiment. We learn from each other, and theory and experiment really go step in step, and it's a very healthy field.
Thanks. So what exactly is the question?
Just introduce yourself and explain a little bit about your research.
Okay. So I'm Randy Hillett, and I'm a cold atom experimentalist. And most of my, even though my background is in atomic physics, most of my physics interest these days is really more many-body physics. So we're studying how bosons and fermions behave collectively at very quantum mechanical conditions at very low temperatures. So we're studying things that are really more condensed matter oriented, using optical lattices to study periodic potentials, and studying fermions in one dimension, and pairing phenomena and Bose-Einstein condensation.
All right, so for you guys, with going forward with your research, what are some of the major obstacles you think you're going to come up against? Say, are they technical? Are they more fundamental? What are you going to run into in the future?
Well, technical limitations are always present, and so we're not going to be getting to femtokelvin anytime soon. But I mean, there's plenty of things to do that are still within the technical limitations that we have. So in my field of study in particular, what we're trying to see is D-wave superconductivity. So one of the things that's kind of an embarrassment to physicists is that after 25 years of studying high temperature superconductivity, we still don't know how it works. And that's not a good, that's not a good thing for after having spent thousands of people having spent the last 20 years looking at this subject. And so one of the things that we're trying to do is understand what is the glue that causes very strongly interacting fermions to want to pair up. And in order to do that, in order to test some of the fundamental models, nobody has solved a model for high temperature superconductivity, but there are some proposals. And nobody even knows these very simple proposals called the Hubbard model. They don't even know if that supports D-wave pairing or not, which is a hallmark of high temperature superconductivity. So one of the primary goals that we have, longer term goals, is to see if there is D-wave superconductivity, D-wave pairing in these systems. And to do that requires attaining very low temperatures, probably around a nanokelvin, thereabout. So we do have to push the envelope to be able to go the next step. We have to go a little bit colder than we're at now, maybe a factor of 3. And so technical limitations are always there. And one of the challenges and probably one of the most satisfying thing about experimental physics is being able to devise ways of circumventing some of these fundamental issues and technical challenges.
I think sort of take the long view of AMO physics. A major theme that I see, at least, is a control of physical systems. That's a lot of the techniques that are developed, the applications that come out of it have come from being able to control all the states of an atom, all the states of a molecule, or light. Creating a laser was really about engineering the optical field. Talking about atoms, which is where a lot of the effort in AMO is. With the advent of the laser, we were able to control the internal states, the electronic states of the atom. We could put the electron up or down, do whatever we wanted to it. And you take that to its logical conclusion and get what Barry does, where he can get those electrons and make them dance microns away from a nucleus. And then with the advent of laser cooling in the late 80s and 90s, which got a Nobel Prize in the late 90s, that was controlling the external state of the atom. So we could manipulate the electrons, but now we could also control its momentum. We could put it where we wanted it to. We could dial in its velocity. We can cool it down. And so now, like Randy's talking about, you can put atoms in lattices and regular arrays of light. And so I think there's this continuous move just to control things better, to really be more, to engineer your systems, control every single piece of it so you could dial in exactly the interactions you want, the Hamiltonian you want, the density, the temperature. And every time we do that, we're able to do amazing things like make precise measurements of the certain energy levels that turn into an atomic clock, or engineer a model of an interaction that's important for a condensed matter system. So this ability to control things, I think, is not unique to atomic physics, but I think it's a real strong point, and has really allowed us to then go out and have impacts on tremendous other fields. So I think it just will continue to happen. Now there's a big motion towards molecules. Atoms are really interesting, but their interactions are actually very weak, whereas molecules can have dipole moments, and you can have much, much longer range interactions. The same thing can be done with Rydberg atoms. They actually can look a lot more like a dipole and have much stronger interactions. So now we're talking about controlling these systems with long-range interactions, which will open up even new things that we can do. When you're controlling things, you can make them work for you. You can turn them into something like a quantum computer. So when you can really control these states really well, they become building blocks in your machines. So that's the next sort of step that follows on this progression of control and applying things and controlling more.
As you get able to do the control, there are a number of other interesting questions. You can ask the question, how does the quantum world go over to the classical world? So one of the series of experiments we've been doing is by going to bigger and bigger atoms. Of course, if you get them large enough, you think, well, the ball picture of an electron in a distant orbit should work at some point. So we've been trying to look for how far can you push quantum mechanics. Even at n equals 300 with an atom that's 300 microns across, you can actually see quantum effects. So you can actually see quantum mechanics rearing its head in something which is microns in dimension or bigger. So we can actually look at that transition from quantum to classical mechanics and see how that works. And that's kind of fascinating. Another thing you can do is, the atoms I study, you can look at chaos in them. It turns out if the electron's in an orbit, by very short electric field pulses, you can actually cause it to reverse its direction. And if you do it right, you can actually trap it. So you get nonlinear dynamics. You've got a driven atom. It's a paradigm system for classical chaos. And it turns out when you go into the quantum regime, classical chaos actually goes over to quantum order. Because you can't remember the definition of quantum mechanics of the Heisenberg principle is that you cannot say precisely where the electron is and what its momentum is. Whereas in classical mechanics, you can define that. And chaos is defined as ultra strong sensitivity to the initial conditions. So we've been able to show that as you go over, you can get to the regime where classical mechanics breaks down and you get this quantum order from classical chaos. And that's, so there are lots of things we can actually do, as Tom was saying. I mean, this control and manipulation. We've been studying whether or not you can actually get information in an atom. If you put information in an atom, how long does it stay before it's perturbed by some external sources and the information is lost? So there are lots of really neat ways today of controlling atoms. The problem is that you've got to get rid of external fields to levels of microvolts per centimeter. That's a bit of a challenge. You've got to have laser systems which is super, super stable. That's a bit of a challenge. Randy has lasers which are relatively stable to hertz, as I recall, which, that's absolute state of the art of what you do. It's a fascinating field, and there's a lot of things you can do.